Okay, in this segment, we're going to be interested in starting to get a handle on the differential mode gain of our 5-transistor differential amplifier. And we're going to develop a new analytic technique, which is also a good experimental technique for doing so. But before we get into that, I want to think about the effect of the output resistance of our transistors on the gain. And specifically of our 5-transistor differential amplifier. So what I want to do is I want to consider our 5-transistor diff amp. That we've been talking about here with a diff pair, an NMOS diff pair, and a PMOS current mirror. We have M3, V3, M4, VCM. So we're going to imagine that we're in this balanced state of a pure common mode input. M1, M2, we have two currents here, I1 and I2. We have currents in the current mirror of I3 and I4. And of course, these currents are all going to be around IB over 2 in this balanced state. Here we have V out. And in this balanced state, we know that V out is going to equal V3. And we know that I1 equals I2 equals I3 equals I4. It's going to be equal to basically half of the bias current IB. And I want to consider with you two different cases where we consider the early effect of transistors M2 and M4 and their effect on by how much the output voltage moves when we apply some change in input voltage to one side of our differential amplifier. And so I'm going to take my input change and I'm going to apply it to transistor M2. Okay, so what I want to do is I want to draw over here a plot showing the drain characteristics of M2 and M4. So this is going to be I2 or I4 as a function of V out. Okay, and here's VDD. And there'll be some common current here of half of IB. And we know that the quiescent output voltage is going to be basically V3. So it's going to be somewhere up near to VDD. And what we're going to find is that our drain characteristics will cross each other, if we draw them properly, at this point. Okay? So M4's drain characteristic might look something like this. And we have a common source node voltage here, V, and so V might be somewhere, say, up here. And so this is M4, M4's drain curve. And that's right, M4. And M2's drain curve might look something like this. Okay, so there's some finite early effect here, and we've drawn it fairly pronounced. And what we want to do is we're going to increase the voltage on M2 by some delta V2. Okay, so we're going to put some additional voltage into the M2 side, and that will increase the current flowing in I2 by some amount, which we could call delta I2, and that current has to be compensated for by an equal and opposite change in the transistors in M1's current. So I1 is going to change by minus delta I2. Remember, it's basically a zero-sum game down here, where the two currents have to add up to IB, which is nominally a constant. And so if we increase I2 by some delta I2, we have to decrease I1 by that same delta I2. And so the current in I3 is going to be subtracted by delta I2, or reduced by delta I2, and likewise that'll get mirrored around here, and so I4 will be subtracted by delta I2. And so what we'd like to do is see how these curves shift. Okay? So let's assume that delta I2 is not very big, and so let's say delta I2 is this amount. So that we have an increase in delta I2 up here. So IB over 2 plus delta I2 would be up here, and IB over 2 minus delta I2 would be down here. Okay? So I4 is going to shift down by delta IB over 2, which means that roughly we're going to see something more like that for M4. And at the same time, M2's curve is going to shift up by that same delta I2. So roughly speaking, it's going to look something, I mean, V is going to increase a little bit as well. So if we were taking both of those things into account, that one might look something like this. Okay? And what's going to happen is that these two currents will have to balance each other at the output. And so the new place where these two currents balance is going to be with the place where these new drain characteristics cross each other, which is right here. And so V out will become V out minus a delta V out here, where this shift is delta V out. So we've moved this curve up, we've moved this curve down, and this new intersection point has moved over here. Okay, so we've increased the current flowing through M2. That's going to wind up pulling down on the output, and the amount by which it goes down is going to be basically this amount in this case. And what I'd like to do with you is consider what would happen if we made these curves steeper or shallower. Okay? And so let's suppose we make them somewhat shallower. I'm not sure here what the best way to do this is going to be, but maybe we can do that down here. So here's V out, here's I2 and I4, here's V, here's VDD, here's our V3. Let's say this is our IB over 2. Okay, and so here is our M4's drain characteristic on a shallower angle, so this would be less significant early effect. And let's say this is our M2's drain characteristic, also on a somewhat shallower angle here. And we're going to assume sort of a comparable change in I2. So we have our delta I2, delta I2. And so we're going to make M4's current, take them up to here. We're going to make M2's current I'm sorry, these arrows go the wrong way. So we made M4 go down and M2 go up. Let's try that again. So M2 goes up, M4 goes down. So M4 going down looks something like this. And M2 going up would look something like that. So the original crossing point was here. So M4 has gone down. M2 has gone up. And the crossing point has shifted over to here. And you can see that this change in the output voltage is more than this change in the output voltage. And you can imagine that if these curves were dead flat, then we'd have even more of an output voltage change, or more significant output voltage change. And if they were steeper, the amount by which the output has to change is going to be much less. And so the slope of this output characteristic is just 1 over the early voltage resistance, or the early effect resistance. And so the higher the early effect resistance, the shallower the slope, the more the output voltage changes for a given input voltage. And what we'll find out is the output voltage is actually, or the output voltage change is actually going to be directly proportional to the incremental output resistance of the circuit. Okay, and so that's kind of how the basic idea works here. Okay, so I want to develop this this technique which I mentioned, which is applicable to any circuit. And it's going to look kind of abstract here at first, but we'll get some very concrete examples before we're done with this segment, and hopefully that will help. And so this technique is called node fixing. So incremental voltage gain by node fixing. And we have here a circuit, which we'll abstractly represent as a box. And we have here an input port and an output port. And we're going to imagine that we've attached here an input voltage source. And what we're interested in doing is basically applying some small change in the input voltage, and that will create in general some change in the output voltage. And we're interested in what is the gain of the circuit, A, which is officially basically the partial of V out with respect to V in. Okay, that's the slope of the tangent line to the voltage transfer characteristic. And we're going to approximate that by a finite ratio of finite differences, delta V out over delta V in. And we're going to assume that our delta V in and delta V out is sufficiently small that this approximates to very well the first order partial derivative here. And also that these changes are going to be small enough that our circuit will be an incrementally linear system eventually. Okay, so you might be able to measure this directly or calculate this directly, but what we're going to do instead is to take something of a different tact. Okay, so we're going to imagine before we apply our change in the input voltage source, what we're going to do is we're going to imagine taking an auxiliary output voltage source, and we're going to think about attaching it to the output voltage port. And we're going to imagine pre-adjusting this output voltage source so that this voltage value precisely matches the open-circuited quiescent output voltage of the circuit. Okay, so we've measured this with an ideal voltage meter, we've recorded its value exactly, and we've dialed this voltage source's value to match it precisely. So that when we attach our output voltage source, there is no current flowing out of the circuit. Okay? You can imagine, if you like, having a resistor here and saying, well, if this voltage is the same as this voltage, how much current flows through the resistor, and then take the limit as that resistance goes to a short circuit, if you like. But basically, if this voltage is exactly the same as this voltage wants to be, there should be no current exchanged between the voltage source and the circuit. Hopefully that's reasonably intuitive. And so, just get rid of this line here. And so, instead of letting the output voltage do what it wants to, we're now constraining the output voltage. And this is the idea of node fixing. We're fixing the output voltage, which might be a node in the circuit. And so now if we apply our input voltage change, the output voltage wants to change, but it can't. And so the circuit is kind of an unhappy circuit. And it registers its dissatisfaction with the state of affairs by producing an output current I out. And that output current, if we were to let the output voltage go, in other words, disconnect our output voltage source, that current would charge or discharge whatever parasitic capacitance was there to move the output voltage to whatever the new quiescent output voltage wants to be. Okay? So instead of disconnecting the output voltage source, what we're going to do is we're going to readjust V out so as to make so we have a plus delta V out here, so as to basically restore the output current to 0. And that will make our circuit a happy circuit, because that state of affairs where the output voltage here not exchanging any current with our output voltage source is precisely the new open circuited output voltage. That's where the circuit wants to be. Okay? So that's the basic procedure that we're going to follow here. Now, we can write in general the output current I out as a function of, I out is going to be a function of two things. I out is a function of both V in and V out here. And if we imagine this as a surface, right? So we have it here, a surface that's a function of two variables. We can imagine around this point of the quiescent V out and I out having sort of a small change in V in and a small change in V out, and thinking about the behavior of that surface in a neighborhood of V in, V out by using a tangent plane approximation. So I out, we can say, is going to be I out, say plus delta I out is going to be I out V in plus delta V in, comma I out, rather V out, plus delta V out. And we can represent this as we can do a Taylor series expansion effectively of this function I out of the two variables, and that's going to be approximately the original I out evaluated at V in, V out, plus a first order partial di out dV in evaluated at V in, V out times delta V in plus di out dV out evaluated at V in, V out times delta V out. And then there'll be, second order terms here that it'll involve, d squared I out dv in squared di out dv in dv out, or d squared I out dv in dv out, the mixed partial derivative, and the d squared I out dv out squared involving these delta v in delta v out, delta v in squared, and delta v out squared. But we're going to assume that the changes are sufficiently small that we can ignore those higher order terms. Okay? So a couple things to note here. One is that we can subtract off the constant term, which in our original case was 0 anyway, so that we can write delta I out, the general change in I out in the neighborhood of this operating point is basically delta I out dv in times delta v in plus di out dv out times delta v out. Now, a couple things to note here. One is that these are partial derivatives, and so when we take a partial derivative, di out dv in, this partial derivative is taken with v out held fixed. All other parameters in the circuit, all other variables in other dimensions are held fixed when we take this partial derivative. Likewise with this one, di out dv out is taken with v in held fixed. This particular partial derivative is the change in the output current that we get due to a change in the input voltage. And this is classically what we call a transconductance gain. So we're going to call this capital GM, and this is the transconductance gain of the circuit as a whole, evaluated under the condition that the output voltage is held fixed. And our positive sign of the current is current flowing out of the circuit. Okay? This is related to something that we've talked about before. So this is a change in the output current, a change in the current flowing out of the circuit for a change in the output voltage. Now, that is formally related to a driving point conductance of the output port. So it's a change in current for a given change in the voltage at that same point in the circuit. Our sign convention for an input, like a port voltage or a port conductance, driving point conductance, is positive current flowing in. So this is going to be basically minus what we might call G out minus the incremental output conductance of the circuit, or minus 1 over R out. Right, the minus sign comes from the fact, again, that for one of these driving point conductance or resistances, positive current has to flow into the port instead of out of the port. And so our delta I out we can write as basically GM times delta V in minus 1 over R out times delta V out. And we're not going to be interested in general output currents in our particular case here, because we're interested in what is the open circuited output voltage. And we argued that that was the one, that combination of delta V in and delta V out was the one that was going to make I out equal to 0. So we're interested in the combination of delta V in and delta V out that makes I out equal to 0 amps. In that particular combination, we can basically solve this equation here for the particular ratio of delta V out to delta V in that makes this equation true. So if we take that over here, we can solve for delta V out to delta V in. So if we move this to the other side of the equation, and we have basically delta V out over R out equals GM delta V in. We move the delta V in downstairs over here. We move the R out upstairs over there. It's basically equal to GM times R out. And this is the gain that we're interested in computing. So this says that the voltage gain, the open circuited voltage gain of the circuit, we can decompose into the product of the incremental transconductance gain of the circuit with the output voltage held fixed times the incremental output resistance of the circuit. And note that the incremental output resistance of the circuit is computed, again, because it's a partial derivative here, with the input voltage held fixed. That basically means that we can, when we compute the GM of the circuit, we don't have our delta V out applied. And when we compute our R out, we don't have our delta V in applied. And so this is another instance of divide and conquer. Kind of like we had when we had source splitting and superposition. We're using superposition here. This is effectively superposition, saying that we have two components or two sources, and we can compute by superposition the overall result of the circuit by the summation of these two separate components. This is a manifestation of superposition here. But we can compute these transfer functions separately, and they basically, the component of delta I out due to each one that we compute, superposed to 0. And the fact that these are computed each with the other source held fixed means that these computations are going to be simplified relative to what they might have otherwise been. And so this is very, very fast and very abstract at this point. There'll be a handout that you can read that talks about it, but I also want to show you a couple of examples in a slide deck, and you'll be able to get this off the course website as well. But you've seen this this data here before. This is again part of a presentation that I gave on this class, and this is a source follower voltage transfer characteristic that I showed you the other day. When we were talking about the large signal analysis of the source follower. But what I want to do is I want to compute the incremental gain of the circuit by this node fixing technique. So here we've got the input voltage coming into the gate of our source follower transistor, and we fix the output voltage at whatever the quiescent output voltage was going to be. It's a bit below, it's roughly a VB below Vn. But that input voltage change is a gate voltage change, and that's going to give rise to a change in the current flowing through our source follower transistor of the little gm of the transistor, the transconductance gain of the transistor, that's di sat dVg, times the input voltage change. And that current is going to flow into our output voltage source. All of it is going to flow into our output voltage source. And so our delta I out is going to be gm, little gm, times delta Vn. And so the overall transconductance gain of the circuit happens to be the transconductance gain of this transistor. Okay? So capital GM we're going to use as a symbol to denote the transconductance gain of the circuit as a whole. And that's delta I out over delta Vn, and in this particular case it's just little gm. Okay, so what about R out? Well, to calculate R out, what we do is we basically turn off the input voltage change. And so this is going back to the quiescent input voltage. And we're going to use our test voltage source here that we've hooked up to the output to probe the incremental output resistance of the circuit. We're going to add a little delta V out and see how much delta I out flows back into the circuit. Well, here we look into the circuit and we see two things in parallel. We see the drain terminal of the bias transistor, and we see the source terminal of the source follower transistor. And so we would see the incremental output resistance or incremental resistance of those two things in parallel. If we are neglecting the early effect in this saturated bias transistor, then this is an infinite incremental output resistance. It's like a current source. And that appears in parallel with the source conductance of the incremental source conductance of our input transistor here, our source follower transistor. And so if we put an open circuit in parallel with anything, it's just the thing that we're putting it in parallel with. And so the incremental output resistance of the circuit as a whole is going to be just 1 over the incremental source conductance of the source follower transistor. Now it may bother you that I have this current increment flowing back up into the source of the transistor and into the drain, or on out the drain. And you have to realize that this is an incremental current. And so there will be a quiescent current that's always flowing from drain to source here, but we're going to represent a reduction in this current as an increment flowing against that quiescent current. Okay, so that's something that takes a little bit of getting used to, but it's a very useful way of thinking about the current increments and how they flow through the circuit. So by node fixing, the voltage gain of our source follower should be the product of these two things. So GM times R out. Well, GM over GS at all current levels is kappa. And of course, kappa is what we found via large signal analysis. So that doesn't prove anything other than in this particular case it happens to work out that way. I also want to show you another example, and this actually is something you'll be doing in Lab 8 in the second experiment. So this is our 5-transistor diff amp, and this is some actual experimental data that I took for this presentation on this particular circuit, which I actually made from some ALD 1106s and 1107s, and I measured these data using one of the SMUs from the class. So this is precisely the kind of thing that you'll be doing in simulation in Lab 8. The basic idea here is that we're looking at a value of V2 at 2.5, so that's sort of our common mode input, and we're applying a delta VDM, or a VDM, between V1 and V2 with one channel of our SMU, and we're hooking up the other channel to measure the output voltage. So this is going to be sourcing current measuring voltage, and we're interested in directly looking at the voltage transfer characteristic. And what we get when we do that experiment, when we sweep channel 1 in fine increments around channel 2, is we get this voltage here, output voltage starting at around 1.5, and then as we get within a 5 millivolts or so of 0, we get a very rapid increase in Vout, and then Vout will saturate up near to VDD. And if we have enough points on this curve, we can approximate the slope of the tangent line by just doing a curve fit, straight line curve fit to this region, and we find the slope of this curve here in the neighborhood of 0 as 371. So this was a bias level at 0.7 volts, which is just about at threshold in this particular case. And so in the next part of the experiment, what we're doing is we're basically setting the input differential voltage to 0 and sweeping Vout, measuring the current flowing back into the output of the amplifier. And so this is the output IV characteristic. And what you see is a very shallow curve here, and then it starts going up pretty rapidly as we get near VDD, and it starts going down very rapidly as we get down near where the output voltage bottomed out or started saturating on the negative end. And the incremental output resistance here around where Vout is equal to 0, it actually crosses 0 here at about 3.3 0.35 volts or something. The slope, 1 over the slope of this line is 19.4 megohms. So that's experimentally what the incremental output resistance of this circuit is, in the vicinity of I out equals 0. Okay, so what we're going to do then is to set our output voltage source equal to that 3.35 volts, which was the quiescent output voltage that the circuit wanted to operate at. And we're going to measure the output current as we sweep VDM. And so this should be our hyperbolic tangent, or hyperbolic tangent-like curve, our differential output current of the diff pair turned around and subtracted. And what we see is a nice saturating IV characteristic, just like we said we would get. And the slope of the tangent line to this curve is going to be our incremental transconductance gain of the circuit as a whole. So in this case, the slope of this tangent line is 18.8 microamps per volt, or 18.8 microsiemens, or micromhos if you prefer. And so the product of these two numbers, Alexa, what is 18.8 times 19.4?
18.8 times 19.4 is 364.72.
Okay, so experimentally here, I have about 365 for the product of my GM times R out, and the direct voltage gain that we got from the voltage transfer curve was 371, which is pretty close. It's about, oh, I don't know, was that a change of about 6 in about 300? That's probably 2%. If we go to an above threshold bias condition, so we move VB up to 1.2 volts and repeat the same experiment, here's the voltage transfer characteristic. The slope of the VTC directly is 106. The output IV characteristic looks like this, and you can see the slope of the tangent line here. In the shallow region is 454 kiloohms, or 1 over the slope of this line is 454 kiloohms. And here there's a new quiescent output voltage, which is where we're taking this, where we're fixing the output for this current to voltage, or voltage to current transduction curve here. And you can see that with the above threshold bias, we have a wider linear region here before it saturates, and the slope of the tangent line here is 229 microamps per volt. Alexa, what is 0.229 times 454?
0.229 times 454 is 103.966.
Okay, so you can see that the product of GM times R out here is about 103. And so the direct slope of the tangent line to the voltage transfer characteristic was 106, and by GM times R out we get something in the neighborhood of 103. So again, we're off by about 3%, which is not bad. So this is experimental data that was taken with kind of homebrew instrumentation. You should be able to do actually quite well if you're careful with being consistent about how you take your simulation data to get something actually quite close. I think I've been able to get it within 1% before, but it's actually quite a nice technique, both analytically, as we'll see next time. We'll get into how to actually think about using it as a circuit analysis technique, kind of a divide and conquer using superposition to analyze a circuit. It's also quite a nice experimental technique, and so you'll be doing something very much like this in LT-SPICE in experiment 2 in lab 8. Okay, that's it for now. This one has gone a little bit longer than I might have liked, but I thought it was important to get through all of this. So Thanks a lot.